Hi guys, welcome back to the vlogs. It's been a while. We didn't miss you, but okay, bye.
Okay, we're going to talk about chapter 10, which deals with solids. Okay, solids. Today it's going to talk about three-dimensional figures, cross sections, and drawings. Okay, there are only 5 sections in this chapter. It's really not that bad. And all of my slides are pretty short because I'm going to add stuff to it and talk kind of a lot. Yeah, that's fine. I'll take care of it in a second. Okay, so solids. We have lots of different solids. Yes. We have spheres are a solid. Yes. Okay, spheres. A sphere is made up of what? What is it closest to?
Circle.
Circle. So if I cut this in half, right, I get a circumference because I have a circle that's an intersection in there, okay? So I can do some stuff with that. I have cylinders, okay, cylinder. Cylinders are what shapes up here and up down here. Circles, okay? So I'm dealing with circles again when it comes to cylinders, and then I'm going to deal with some other stuff with them. I have cones. Cones are what shapes? And circles. So the bottom is a circle, and if I divide it, I can make triangles out of it, yes? Okay. I have pyramids. Pyramids are what shapes?
Circle or triangle.
Triangles and a square. The base is a square. Okay. I have cubes. Cubes are easy. What are they? Squares. And you have rectangular prisms. And rectangular prisms are rectangles and squares. Okay? Do I have formulas for all of those things?
Yes, of course you do.
Yes. So that means that if I think and use my brain, I can break some stuff down. Okay? We're going to look at these more in a little bit. Okay? One of the things that we want to talk about when we're dealing with 3D objects is something called Euler's theorem. Okay? Euler's theorem. In all 3D objects, I have faces, edges, well, not all 3D objects, but I have faces, I have edges, if it's a polyhedron, okay? A polyhedron would be a shape like one like this. This is not a polyhedron. Why is this not a polyhedron? What do you think compared to this? Because it's rounded, okay? Polyhedrons have distinct edges and vertices, okay? And if I have polyhedrons, I have faces, edges, and vertices, okay? How many faces on this object do I have? 5. 1, 2, 3, 4, 5. Okay? How many vertices do I have? 5. 1, 2, 3, 4, 5. How many edges do I have? 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Euler's theorem says F equals the number of faces, V equals the number of vertices, and E equals the number of edges. And it gives us this formula that tells us if I take the faces plus the vertices, it should equal the edges plus 2. Okay? How many faces are here again? 5. 5 faces. How many vertices are here?
5.
What's 5 plus 5?
10.
How many edges did we say there were? 8. And 8 plus 2 is?
10.
So the faces plus the vertices equal the edges plus 2. Which means if I know one of them, I can find out the other 2. I can work my formula backwards to solve for those. Okay? And we're going to have to do that eventually in a little bit. Okay? You can only use Euler's theorem on objects that are polyhedrons. Okay? Not on objects such as cones or cylinders or spheres. Anything that's rounded is not considered a polyhedron. It has to have vertices. Okay? On this right here, okay, let's count the faces. How many faces do I have on this object? 6. Okay? I have 6 faces. Okay, if I have 6 faces, how many vertices do I have? 8. 2, 4, 6, 8. What's 6 plus 8? 14, so how many edges do I have?
16.
No.
12.
Yes.
12.
12. Because you have this. You had faces, which you said were 6, right? And 8, right? Equals my edges plus 2. So I had 14 equals edges plus 2. You subtract 2, and your edges equal 12. You're gonna have to set it up in that formula and solve. That's why I put it behind my back, so you had to think. So you couldn't sit there and count it. Okay? But that's how I can solve some things and figure things out. Okay? If I know how many edges I have and I know how many faces I have, I can figure out how many vertices I have. If I know how many edges I have and how many vertices I have, I can figure out how many faces I have. Okay? It's kind of nice that I can do that, and then you don't have to sit there and try to visualize it or count things up the whole time. Makes it a little simpler. Okay. So we know that a sphere, a cylinder, and a cone can be formed, okay, by rotating some familiar 2D shapes. So we talked about how a sphere is basically has a circle that's being rotated, right? We talked about how a cylinder, okay, if we rotate a square or a rectangle about its side, we can create a cylinder. So if I take a square, I don't have just a square, but if I had taken a square like this, oops, you take just a square and you rotate it from one side to the other, like using this as your rotation, and I rotate this around, I'll create a cylinder out of it. Okay? And if you take a triangle and rotate it around, okay, think about this. If I have a triangle that's like this, right? And I rotate this triangle around, what shape do you create? A cone. A triangle is a cone, right? Because I can take a cone, and if I take this like, I need a pencil, because it's thinner. If I take this cone and I put my pencil in it, right, and create the 90-degree angle here, do you see how that creates a triangle, right? Okay, and if I rotate that triangle all the way around, I create that circumference of the circle, which gives me the cone. Yes?
How would the square make a cylinder?
Ooh, I need a shape that, I need just a square to show you. A square and a rectangle can make a cylinder. Because basically, if I have a square, it's like standing up like this. If I rotate it,
Oh, okay.
does that make sense?
Yeah, okay. Was everyone else confused about that?
Yeah.
That's fine, but does that make sense
Yeah.
now? Like that? Okay. So that is what I'm looking at when I'm dealing with these 3D objects, okay? So we're going to identify number of faces, edges, vertices, and different types of polyhedrons using Euler's formula, okay? You can do it when something is stacked on each other too. Let's say, I'm gonna hit something. Okay, here we go. Let's say that I have two of these. Ooh, brand new one. I haven't opened this one. Okay, let's say I have this. Okay. A shape that looks like this.
A diamond.
Okay, a shape like this. And I want to know how many vertices, edges, and faces this shape has. Okay, what are we going to do?
Couldn't you just cut it in half and and double it?
Well, sort of. Sort of. These two right here, okay, if I cut it in half, how many faces does this have? 5. If I put it together, how many total faces are here?
9.
9.
Oh.
Because the base is shared.
Oh.
Because this base, the square base, is shared, yes?
Yes.
Okay? So it changes how many faces I end up having from, actually, I don't even have 9.
No, you have 8.
I have 8.
Well,
Because-
that's right.
Oh, did you say 8?
Yeah.
I thought, okay. I don't have a face here anymore. I took away that bottom face because it's combined into one object. So, you have to like think a little bit through this stuff, okay? If this is just a normal pyramid and there's a bottom base to it, it has 5 faces. But if I put 2 pyramids together, I end up taking away that bottom square face because they're all connected. So now I have these 4 faces and these 4 faces, okay? How many vertices do you have on this? 2, 4, 5, 6. How many do I have when I have this?
No, 5.
5, okay? There's a difference. How many edges do I have here?
Would you count
4,
that as
4, and 4. So
12.
12, okay?
And 6.
I have 12. These only count as 1. Is that what you were asking too?
Kind of. I was asking the top ones.
Yeah, this is
1.
1, 2,
Okay.
3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, there are 12. So there are 12, okay? So you need to be able to recognize that and figure some things out off of that. Okay, so here's the deal. Something called a cross section. We need to talk about what cross sections are. In any 3D object, there are things called cross sections, okay? Cross sections are sections that create a shape inside of our 3D object, okay? When I take this sphere, and if I placed a sheet of paper through here, what shape would I get? I would get a what? Not a half circle. If I put a piece of
A
paper
dome.
in here and it comes, no,
A circle.
I would get a full circle. If I just throw a piece of paper, because paper is what type of, is it 2D, 3D, what is it? If I put a piece of paper through here and cut this, I create a circle, yes? Okay, the paper creates a circle. Not the actual object is a circle, the object is just 2 spheres cut in half. But that cross section creates a circle. Cross sections create 2D objects inside of something.
Oh, I understand.
Okay. If
Yeah.
I threw, okay, so a cross section is the intersection of a solid and a plane. It's taking a solid and cutting a plane through it. Okay, you remember what a plane is? From chapter 1? Okay. A cross-section forms 2-dimensional figures. Often people refer to a cross-section as being a slice of a solid. Okay? The type of 2-dimensional shapes formed depends on how the plane intersects with the solid. If I took a plane and put it through here, let's say I take this and cut it in through there like that, what shape would I get?
A triangle.
A triangle. I would get a triangle, okay? So it depends what happens. If you have an equal, you get equilateral triangles. You do not get you do get non-equilateral triangles sometimes. If it's diagonal through it, you're gonna get a non-equilateral triangle, okay? If I have a hexagon, or if I have a cube again, and I just angle it different, you can get hexagons, you can get rectangles through things, you can get pentagons through things, you can get lots of different shapes and objects. You just have to look and see how it's cut. And on your book, they're gonna have everything shaded darker, and you'll have to tell me, like, what shape does that make when this cross section goes through it, okay? The other thing that we can talk about is Pythagorean theorem when it comes to this. So, because I have a cube right here, I'm going to talk about this. If I take a cube, right, and I create a diagonal through this cube, like this, okay? I create that diagonal, I have this, and I have this line coming here like that, right? What shape do you create? Triangle. So I can use Pythagorean theorem in a different way here. It's going to be a little different than what you're used to, okay? I'm going to use something called well, yeah, I'm gonna use the Pythagorean theorem, but it's going to be h squared equals a squared plus b squared plus c squared. Because here's what we're gonna use. If I take this diagonal through here, my diagonal that I cut is my h squared. So this is my h squared. Your a squared is this edge here. Your b squared is this edge here. Your c squared is this edge here. Because you're making a 3D triangle inside of there still when you cut through it. Okay, still, if I cut through an object, it creates the plane that cuts through it creates a two-dimensional object. But when I cut a 3D object, I still have two 3D objects. Yes, like if I split them in half, I have half a sphere and another half a sphere. Or I cut this in half and I have whatever. So this is h squared, your diagonal, a squared, b squared, c squared. That you create that triangle, okay? And you can start to solve for things doing that. Okay, one last thing I can. Let's get this back on. So, we already went through that, that's okay. Okay, so Cavalier's principle, okay, says two solids with the same height and the same cross-sectional area, okay, meaning if I slice something in half, whether they're the same shape or not, okay, if it's a cone and I slice it in half and that circle that you create 2D in a cone has the same area as a cube that you cut in half has the same area as that square. If they have the same areas and the same heights, if their cross sections have the same areas and their heights are the same, okay, then their bases have the same volume. Meaning a cone can hold just as much as a cube, liquid-wise or whatever you're putting into it. If I cut this, if this height is 12, okay, and the height of this cube is 12, and when I cut this in half, right, or slice through it and create a cross section, and that circle's area is 16, and this square's area is 16, they both can hold the same volume. Okay? So that's why when we do packaging and things for companies, sometimes the shapes of things change because it may seem smaller, right? Like, to me, this cone seems smaller to hold than this cube, yes? But if they hold the same volume, why wouldn't I give the consumer the cone and also save marketing costs by less plastic or using less material or whatever? Does that make sense? So that's where you'll see this type of math used a lot, is in marketing areas and pitches like that. Yes?
So it's not the area of the...
It's not the area of the object, it's the area of the cross-section that's created. Okay, so that 2D object that's created in it. So right here, see how this has the cross-section of like a parallelogram, and this has a cross-section of a rectangle, okay? So this area here and this area are the same, plus these two heights are the same, then the volumes are equal to each other. So meaning, if I know the volume of one object, and they give me the height of the other object, and want to know, or want me to figure out what the height of the other object is, something like that, I can work the problem backwards because they are equal to each other. Okay? And then, similar solids theorem. If two figures are similar with a scale factor of x to y, then their surface areas have the ratio of x squared to y squared. If I have similar figures, and the ratio is 1 to 2, their areas are 1 squared to 2 squared. Because an area is squared in the first place. So your areas become squared towards each other. Their volumes become cubed, which makes sense because when you do area or volume, you're doing squares of things or cubes of things. So if I have two objects and it says it's a 2 to 4 ratio and they're similar, then that means the area of similarity is 2 squared to 4 squared. The volume of similarity is 2 cubed to 4 cubed. Does that make sense? Okay, so those are the things that you're working on your homework tonight. Cool? Okay.
Like, subscribe, comment, tweet me at David Dobrik. Anything else to add, Korea?
I'm tired.
Okay, you're late.